Good day and welcome back. This is part 4 of our video series on lines and planes. So this is where we would be starting kind of our second day in class discussing lines and planes. And what I would typically do is begin with a review of these key concepts. And it's never a bad thing to do this. So a line is determined by two quantities. You need a point on the line and a vector, let's call it v, representing the direction of the line. So think kind of a point and a slope in pre-calculus. And there's three basic equations of the line. We start off most simply with the vector equation. So a point x, y, z on the line satisfies the following. The vector x, y, z is equal to the vector determined by the point on the plane plus t times the direction. And we can go from the vector equation to what we call the parametric equations by simply equating the like components. So on the left, the first component is x, and on the right, if you were to maybe distribute this t and combine into a single vector, that first component would be x naught plus at. The middle components would be y and y naught plus bt, and from the third components, z is z naught plus ct. And we'd refer to these as being the parametric equations of the line, the idea being that for each value of t, which we'll think of as a parameter, you get a different point on the line. And lastly, we can modify this a bit more to get what we call the symmetric equation of the line. If we were to isolate the t in each of those three parametric equations, it would have to be the same t value. So x minus x naught over a in the first, y minus y naught over b in the second, and z minus z naught over c in the third. Then if we simply disregard the t, we would have the symmetric equations of the line. And note, it's powerful to have these three different perspectives, and depending upon what the question asks for us to give or what we need to do to solve the problem, one of these three versions may be more conducive to work with. The next topic we discussed was planes. We said similarly, a plane is determined by a point on the plane and a vector normal or perpendicular to the plane. And here there's really just one big equation that we would write down. So it's a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And any point x, y, z that satisfies this equation would be a point that lies on the plane. The further observation that we want to make is that if we were to take this a bit further, kind of for future use, if we ever see something of the form ax plus by plus cz equals a number d, this is a plane, and we can immediately pick off this normal vector. It's the coefficients of x, y, and z, respectively. And oftentimes in the future, we will encounter planes in this form, and we'll have to recognize it is a plane and write down the normal vector. So with this introduction out of the way, let's look at another example. Let's find the line of intersection of the following two planes. And note, both of these planes fit precisely into this form that we've indicated above. So we can immediately pick off the normal vectors of these planes. So let's say for the first plane, we'll call it N1, would be 1, 1, and 1. And for the second plane, let's call it N2 for the normal vector, would be 1, 2, and 2. So the first thing, let's kind of draw a generic picture. Whenever we can draw a generic picture, it's probably not a bad thing to do. At the very least, we might get a little bit of intuition. So we are looking for the line of intersection of two planes. So I'm going to draw, kind of what I might think of as just an arbitrary plane. And then for fun, what I'm going to do is go ahead and draw a line on this plane. So roughly speaking, let's just say our line looks something like this. And I know this looks probably really awkward, kind of going off the sides of the planes, but we'll see why I'm drawing it this way, hopefully in a minute. So one observation I want to make is if the line L is on the plane, then the normal vector of the plane is going to be perpendicular to the line. So we'll come back to that observation, but I'm going to erase that vector for a moment. So we're looking for the line of intersection of two planes. So there's going to be some other plane, and we're assuming it intersects our plane at this line L. And I've made some of those lines dashed just to give the impression, hopefully, here of depth. So there is a line of intersection of these two planes. And if we want to find the equation of that line, we need the two kind of key things that we've been looking for. So we need a point and we need a direction. And in this case, what we're going to do is start off by finding the direction vector of this line. And the observation to make is what we alluded to earlier, that the line L is perpendicular, or let's say orthogonal, to N1 and N2. That is to say, if you were to draw, much like we did earlier with the green vector, the normal vector to one of these planes, that normal vector must be perpendicular to any line on the plane. So that is the key observation that we need. So because L is perpendicular to N1 and N2, what that is telling us is that the direction of the plane can be determined by taking the cross product of those normal vectors, which we've indicated earlier. So think a 3 by 3 determinant, I, j, and k across the top row, 1, 1, 1, and then 1, 2, 2. And similar to previously, if you were to go ahead and do these computations very quickly, you get 0, minus 1, 1. So we know the direction of our line. Now we need to find a point on our line. That is, we need to find any point we can come up with that simultaneously solves the first equation of the plane and the second equation of the plane. So we need to find a point that simultaneously solves x plus y plus z equals 1 and x plus 2y plus 2z is 1. And in this scenario, what we have is 3 unknowns and 2 equations. So this is something in an algebra class we might refer to as a underdetermined system, that there are actually infinitely many solutions to this problem, and those infinitely many solutions correspond to every single point on this line. So what we're going to do to try to make this simpler for us to work with is we want any point that works. What could be a simplifying assumption that we make? So I want you to think about that for a moment. How can we make this simpler? And if you're thinking maybe setting something equal to 0, I would agree with that. So let's try just making the z equal to 0, and we'll see what happens. So if we make the z equal to 0, which we can't do for free, we're going to have to come back to that, we get something simpler to work with. X plus y equals 1, and x plus 2y equals 1. And if you were to use whatever your favorite method is to solve this, going back to an algebra class, think elimination or substitution, you would very quickly come up with x equals 1 and y equals 0, which you might be able to just get from inspection as well. And that gives us a point on the plane. X is 1, y is 0. And that x equals 1, y is 0 comes from what we came up with here. And then the z coordinate is going to be 0, going back to that simplifying assumption that we made. So a point on the plane is 1, 0, 0. And when we made that simplifying assumption, if you were thinking why not x equals 0 or y equals 0, those would work as well. So just note you can also try or use x equals 0 or y equals 0. Somehow we just need to come up with a point that satisfies both of those equations simultaneously. So we have the point, we have the direction, we now have the line of intersection. So the line of intersection is given as follows, and I'm going to simply write down the vector form since we haven't been asked for a specific form. xyz is equal to the vector represented by the point plus t times the direction, 0, -1, 1. So this completes our example and really completes the material for this video. And if we were in class, this would be kind of our second day or period discussing lines and planes. And this is a point where I would turn the floor over to you all. So in Canvas, underneath the videos associated with lines and planes, you will find a worksheet similarly titled Lines and Planes. And what I would do in class is pass that worksheet out. I would give you probably 30 or so minutes to work through it, turn your desk, talk to your neighbors, discuss, and then we would come back together as a group to discuss one or two of the problems. So in the next video, what I'll do is go over two of the problems from that worksheet that I think are just key examples that are worth understanding. But between now and then, what I'd recommend doing is going to that worksheet, giving yourself a significant amount of time, and practicing examples. One of the difficulties associated with lines and planes is that we can ask so many different questions that really just hinge back on those key ideas. For the equation of a line, we need a point and a direction. And for the equation of a plane, we need a point and a normal vector. So stay tuned and take care.